Hi, how are you? Okay, so I hope that everybody is doing good and yeah, we are learning structure of atoms. Okay, so we have completed 5 lectures of this chapter of class ninth, structure of atom, and we learned many things. Okay, now today we are going to learn few theories. Okay, two theories basically. Okay, one is electromagnetic wave theory and other is Planck's quantum theory. Okay, and we will be knowing the like, see, we already discussed the structure of atom according to Thomson. We discussed the structure of atoms according to Rutherford, okay, and then Bohr's model, but not yet. Okay, so like there's another quantum mechanical model of atom, okay, which is, you can say, the real, almost the real representation of what atom actually is. Okay, so to learn this, the newer, okay, the latest model of atom, you can say quantum mechanical model, we need to first learn few theories, okay, like few things, that what was the you can say the theories, uh, what were the theories and what was the incidents which actually uh, which can say helped scientists in getting through this quantum mechanical model of atom, and in solving many of the you can say mysteries of science. And there were many observations which were unanswered, okay, before this model came into existence, you can say. Okay, so let's start this class. Okay, so I am Ashutosh, and this is a lecture series of structure of atoms chapter, and this is sixth lecture of the series. If you have not watched or completed the previous lectures, just go and watch. Okay, all the 5 lectures are available, and then this is the sixth lecture. So let's start this. So in today's lecture, we are going to discuss these two theories, electromagnetic wave theory and Planck's quantum theory. Okay, so this electromagnetic wave theory was actually, see, it was around late 1800, okay, like 1850, 1870, and scientists were doing experiments based on the nature of the heat. Okay, what are the heat waves, what is the nature of heat waves, okay, I mean, like how they're made. Okay, so like it was all people were discussing, of people of science community, okay, were discussing in those days. Okay, so then uh, Maxwell came up. Maxwell, okay, with his own electromagnetic wave theory, electromagnetic wave theory, and he proposed, okay, nice things, like he proposed that when a charged particle, when a charged particle moves or accelerates, we can say, so it is going to produce, let's say the charged particle is moving in this direction. Okay, so let me denote this charged particle with the mm, this green color, huh? So this charged particle is moving in this direction, red direction, so it will be producing the, due to its motion, okay, these waves in, we can say, this direction. Okay, and another wave like this perpendicular, huh? So they all are perpendicular to each other, see. Okay, it means if we try to draw this all, so this axis is perpendicular to this axis and is perpendicular to this axis. Okay, so if a charge is moving in this direction, let's say red direction, so it will be, you can say, formation of these waves will be there along these directions. Okay, one of them is electrical waves, you can say, electric field, and other one is magnetic field. So we can say that when a charged particle moves, Maxwell suggested, then there will be a formation of waves, electrical waves and magnetic waves, okay, in perpendicular directions to the motion, as well as they are perpendicular to each other also. Okay, and that's, he named it as electromagnetic waves. You will learn this, the properties and characteristics of these waves in detail in higher classes. Electromagnetic waves. Okay, so electromagnetic waves, light is also a kind of electromagnetic waves. Okay, the radio signals, FM signals, mobile, okay, all these are electromagnetic waves. X-rays, gamma rays, okay, all these are electromagnetic waves only. Now, so these electromagnetic waves, actually they do not require any medium. Okay, they do not require any medium for their propagation, like sun, okay, is there, and then we are on earth. Okay, we are on earth, so then in between, okay, so there is no medium. Okay, nothing is there present in the path. Okay, and light reaches to the earth, so it means that they do not require any medium. Okay, so electromagnetic waves. Then he suggested that light is also a, okay, light is also an electromagnetic wave. Okay, it means that light will also have this wave characteristics or not, wave properties or not. Light will behave like a wave or not. Okay, when Newton was there, uh, Newton proposed all the behavior of light, like the reflection part. Okay, how light reflects, okay, when there is a mirror. We all know that this happens. Okay, so it looks like the striker of carom board or not. See, the striker of carom board, it strikes here and then reflected like this. Okay, so it means that light behaves like a particle nature. Okay, so Newton suggested that light behaves like a particle, while like after these electromagnetic waves, and there are different observations based on the wave nature of light, like interference and diffraction. So it was also found that light not only behaves like a particle, but it also has properties very similar to that of waves. Okay, and that's why light has, you can say, dual property. So we can say electromagnetic waves will have dual nature or not, because light is also a electromagnetic wave. Okay, and that's why light will also behave like a particle and wave, and similarly all the electromagnetic waves will behave like these particles and waves. Okay, so this was one theory, electromagnetic wave theory. And so there are some points are there. Like first thing is these oscillating uh, electric and magnetic field, okay, produced by this oscillating charged particle or moving charged particle are perpendicular to each other, and both are perpendicular to the direction of propagation of charged particle. Second thing is, unlike sound waves, the wave produced in water, okay, so the sound waves or the wave produced in water, okay, in this water pond, let's say, on the surface of water pond, they are they require a medium, okay, while the electromagnetic waves do not require a medium and can move in vacuum also. Now, as I was saying that the gamma rays, X rays, ultraviolet, radio waves, microwaves, they all are electromagnetic waves. So we can say that visible light is only a very small part of the whole spectrum. Like we can like if this is the whole strip of electromagnetic waves, okay, based on the frequencies, okay, gamma rays we can write, then X rays like this, okay, and then UV, and then visible, okay, visible, and then infrared, and then microwaves, and then radio waves, okay, like this. So the visible part is, see, very small fraction of, you can say, the whole electromagnetic spectrum or not, okay. We can say that light, the part of electromagnetic waves which we can see is very small as compared to the whole spectrum, huh? So this is called electromagnetic spectrum, electromagnetic spectrum, okay, in which all the waves, electromagnetic waves of all the frequencies are present, okay, clear. And then the last part, that different kinds of unit, like we can use this gamma, sorry, this frequency thing to measure, like, so if frequency, so like is violet is has more frequency as compared to red, okay, in Vibgyor we can write Vibgyor, okay, and then wavelength, so this is frequency we can write. Frequency is measured in hertz, okay, and this is wavelength. So these are the terms which, okay, I'm going to explain these things, okay. So lambda, for lambda, violet has less as compared to red, and we measure it in terms of meter. So like, what is frequency and what is wavelength, okay. So just I'm going to just try to explain this in, see, so I'm going to represent a wave like this, okay. So the distance between this and this point, see, these are similar points or not. The waves started, okay, going up here, and here also it started going up, okay, or the distance between this and this. So from here, like, here it started goes down, going down, and here also. So like, the distance between any of this is called a wavelength, okay, and it will be always equal. So these and these are equal. So okay, this is wavelength, clear. The length of one wave is wavelength. And frequency, so frequency means, like, in 1 second how many cycles, huh? So how many times this happened, okay, is frequency. So frequency means how many times the wavelength, complete wavelength, okay, occurs in, you can say, 1 second, and wavelength is the distance between these. So this is all about electromagnetic wave theory and something about waves. Now the second theory which we are going to learn today is Planck's quantum theory, okay, Planck's quantum theory. So I explained what is quantization in the previous class, okay, where I gave this example of cookies to you all, okay. Like, we cannot buy 6 or 5 cookies if we want. We can only buy cookies in multiple of 8 cookies, huh? like 8 or 16 or like this only. Huh? So there was there's like many things, many observations were there. Okay, and Planck's quantum theory, let me add another page and we will discuss this quantum theory in the next page. So yes, see, so there were like many observations. Okay, like uh, photoelectric effect is one. Okay, photoelectric effect. Do you know that there are like certain metals? Okay, there are certain metals on which if light falls, and let's say there's a so detector. Okay, so detector, let's say this is, and we have a bulb here, let's say bulb here. Okay, so when light falls on this, you can say metal, okay, on this metal surface, so then the electron will come out and which will reach to this plate, this is detector, you can say, and this bulb will start glowing. Simple. There is no circuit complete, no wire there, okay, in between these two plates. But even after this, so light falls on this, electrons ejected, and that electron reaches here, and then this bulb glows. Simple. This is photoelectric effect. Okay, and similarly, when you use more intensity of light, then more electrons will come out, and the bulb will glow, you can say, brighter. Okay, so this was observation. And similarly, there were like many other observations also based on Bohr's model and all, as I explained already. Okay, where these electrons are going to jump to the next higher level and the next higher level. Okay. So like, so this Planck's quantum theory says that energy of any particle. Okay, so see, these light, he proposed that light, it looks like that light is a wave. Okay, light is a wave. Okay, so light is coming continuously. Okay, like a water. Okay, like a river of water or not, like a river flowing continuously. But he proposed that no, light is actually packets. Light is like energy packets. Like now there is no river flowing. Okay, we have water in packets. So there are like different packets in which water is there. Okay, are you getting my point? So if let's say we have a waterfall, okay, we have a waterfall like this from some, okay, hilly area, you can say, and we are enjoying from here this waterfall, okay, very nicely. Now, so this was like continuous flow of water or not? But now Planck proposed that no, there is no continuous flow of water. It is actually, what is this? It is actually, he proposed that there are like small packets falling. Okay, small packets of water, huh? Like this. Are you getting my point, everybody? Okay, like this, it is falling here. So it means that now, so light behaves like a wave, but it will also have a particle nature, and the particle nature of light. Now, so what is the energy associated with each packets? He called these packets as quanta. Okay, in case of light, he called, there's a special name. So quanta for like in general, and for light's purpose, like for light, quanta of light is called quanta of light. He proposed them as photon. Okay, so light quantas are called photon. Otherwise, the smallest quantity, the unit quantity, is called quanta. Okay, like the charge on an electron. So charge on an electron is 1.6 into 10 to the power minus 19 coulomb. Okay, so either one electron will be there, or two electrons will be there, or three electrons will be there. We cannot have 2.5 electrons. Okay, so the charge associated with these two electrons will be minus 2 into 1.6 into 10 to the power minus 19 coulomb, or minus 3 into 1.6 into 10 to the power minus 19 coulomb. It means that this is the smallest electric charge. Okay, and all the other higher charges are multiple of this smallest charge. Clear? So this smallest charge will be called the quanta of charge. Okay, this will be called a quanta of electric charge. Okay, and all the higher charges, okay, will be you can say integral multiple integer, okay, multiplied with some whole number, okay, of this smallest value. Okay, so we can say this is called quantization. This is called quantization. That if we have, let's say, E, the smallest unit, and if we have all the other charges existing as Ne, where N is a whole number, then this is called quantum uh, theory. Okay, this is the part of quantum theory, and this is called quantization. So he proposed that if there is a light, okay, with frequency nu, okay, nu is a Greek letter, okay, nu, okay, so he said that, so the energy associated with the that light wave will be directly proportional to the nu. It means that more the nu, more will be the energy. Okay, then Planck suggested this, Max Planck. Okay, so Planck then introduced a constant, okay, this h, which is called Planck's constant. Planck's constant. Okay, and this was the whole quantization theory, quantum theory, you can say, where he suggested that energy is not a kind of wave, but it actually exists in form of packets. One packet will have this h nu energy based on the frequency associated with the wave. Okay, so similarly, like quantization of charge is there. Okay, and then quantization of energy is there. Okay, if we want, we can say quantization of mass is also there, because the smallest unit of mass is 1 AMU. Okay, so these are like everything exists in form of this quantization. Okay, so he you can say suggested this first, and that's why it is called Planck's quantum theory. Okay, so this was Planck's quantum theory. Now let's go back to the slide. Okay, so these two theories we discussed. Okay, and here let's see this, what is written here. So electromagnetic wave theory, electromagnetic radiation. In classical physics, the flow of energy at the universal speed of light through free space or through a material medium in the form of electric and magnetic fields that make up electromagnetic waves, such as radio waves, visible light, gamma rays, all are part of electromagnetic waves only. And Planck's quantum theory. So according to Planck's quantum theory, different atoms and molecules can emit or absorb energy in discrete quantities only. In discrete quantities, that the energy difference will be like, there's a okay, so like if we want to say this, so like in terms of atoms, let's see, huh? So we have this nucleus, and then there is like first orbit, we have electrons like this, and then we have second orbit, let's say we also have some electrons like this. Now, as I said, as I explained, that there's different energy is associated with these energy levels or not. So we can say this will be N1E and this will be N2E. Okay, N1E, N2E, I am saying because like there'll be some smallest value E, you can say, and the energy will be quantized. So the first orbit will have N1E energy and second orbit will have N2E energy, let's say. So when an electron is going to make a jump from lower energy to higher energy, let's say, so then how much energy we need to supply? So delta E will be equal to, we can write the final energy is N2E and initial energy is N1E. So then we can say N2 minus N1E. So this is a fixed energy or not? Fixed energy or not? Which if we supply, so then this electron is going to make a jump to higher energy level. And that's why it is, we can say that there are like discrete, these N1E and N2E are like discrete values. Okay, you can say specific values. Okay, where we'll be knowing the difference between these energy levels, and that's how we can supply this much of energy. And if an electron coming back, okay, so jumps back to the original energy level, so then it is going to release the same amount of energy. Okay, so absorbed in the form of electromagnetic radiation is known as quantum. Okay, now question. So sodium plus has completely filled K and L. Explain. So we know this. Sodium has 11 electrons, okay, and 11 protons. And so so the electronic configuration will be 2, 8, and 1. So it is going to lose its outermost electron. So then it will have 2 and 8. Okay, that is the K shell will have a complete fully filled configuration. Okay, now, next question. If Z is equal to 3, what will be the valency of the element? Okay, so Z means atomic number. Atomic number is 3. It means that it is it is lithium, first thing, and lithium has an electronic configuration of 2 and 1. So it is going to lose 1 electron, and that's how its valency will be 1. Okay, see. So this is all for today. Okay, I hope that you enjoyed learning, and if you have like I also know that there are like many questions arising in your mind, and you have many queries and you want to ask, okay, those queries. So if you have any doubt, any queries, okay, if you're not able to understand what I explained here, okay, you can post it on forum, you can comment, okay, and then we'll be explaining it further. Okay, so thank you all. Thank you for your time. Keep learning from Ask IITians. Thank you.